start with the regular business. That the first, what exactly does one mean by a dynamical system? So, a dynamical system is a set of n first order ordinary differential equations. So that's what a dynamical system is. So what we mean by the word dynamical system is that you have a set of n first order ordinary differential equations coupled. Otherwise, I mean, it wouldn't make sense. Each separately evolving according to its own, so that would not, having n doesn't make sense. So obviously coupled, linear or non-linear, that depending if it's a linear set, that's what it is. But if it is non-linear, well, that's when life becomes more interesting. So a set of n first order differential equations, if the variables are written as x1, x2 up to xn, so n first order equations means that there are n variables, and I have xi dot for the I running from 1 to n, each one of them some function I of the set of xj. Right? So that is what a dynamical system looks like. Just a set of n first order equations, that is, so n is generally referred to as the dimension of the dynamical system. So a dynamical system of n dimension means that there are n variables x1 to xn, and so all right. Now, first point to note is that there is, it's called autonomous if all fi are explicit, and all fi have no explicit dependence on time. So that's what makes it an autonomous system. It's an autonomous dynamical system. For example, x1 dot is equal to x1 plus x1 x2 plus maybe x1 square, and x2 dot equal to minus x2 plus x1 or minus x1 square plus x2 squared x1, something like that, let's say, or whatever it is. This is an example of, that is what a typical autonomous system would look like. Just functions of x over on the right hand side, no explicit time dependence. Non-autonomous obviously means that there is explicit time dependence on the right hand side. So I have explicit time dependence on the right hand side. So for example, if you write x1 dot equal to x2, and x2 dot equal to minus omega squared x1 minus, let's say, f cos omega tx1, then you have a non-autonomous system. Now, if I give you a non-autonomous system, you can very often, or almost, you can always, with some trick or other, sometimes the trick is straightforward, sometimes may not be so straightforward, but every time I give you a non-autonomous system, you can, if you want, convert a non-autonomous system to a higher dimensional autonomous one. Now, how? All that you need to do is write x3 equal to cos omega t, and then write the set x1 dot equal to x2, x2 dot equal to minus omega squared x1 minus f x1 x3, and x3 dot equal to minus omega square root of 1 minus x3 squared. So here it is. This procedure is never unique, but every time you can find a way of doing it. A non-autonomous system can always be embedded in a higher dimensional autonomous system. So that's that takes care of autonomous and non-autonomous. A very standard example of a dynamical system is Newton's law. So Newton's law tells you, so in one spatial dimension, let's say one spatial dimension, one particle, it is mass times acceleration is equal to some force f of x. So I can write this as x dot is equal to y, and y dot is equal to f of x divided by m. So I can take a second order differential equation, which is what Newton's law is, and write it as two first order differential equations. So Newton's law, the simplest form of first order, a one spatial dimension, one particle system is two-dimensional dynamical system. So that's the, so essentially the fact that one has been encountering it all the time in things which we have been doing, except that we have not been calling it as a dynamical system. So there is nothing very special about a dynamical system. It's just that it is systematizing is often useful, and so that's what one is doing. So the autonomous, non-autonomous, then comes the question of conservative or not. So conservative, non-conservative. All right. So now what to do? I have in this space of xi's, what these equations are telling me then you have specified the velocity, which is the velocity vector, which is this x I dot. So in this supposedly n-dimensional system, you are given a block of initial conditions. So imagine that this is an n-dimensional space. I've given you these n initial points, and you are supposed to track the evolution of these n points in time. So, what's conservative? Conservative would be that if I consider a volume of points at any given instant, so if I have this volume of points over here, then that is going to be preserved as dynamics goes on, which means that there is going to be as much flowing in as flowing out. So the flux is going to be 0. So this volume is going to be preserved. So the flux is going to be 0, which means that the divergence of V vector is going to be equal to 0. So divergence V, so del Vi del Xi equal to 0 identically is a conservative system. There is certainly no doubt about that. If on the other hand, I have this, I can make the statement that divergence V is equal to some constant independent of Xi and is negative, then certainly this volume is going to contract as time goes on, and you have a dissipative system. And if it is positive, then it is a blow-up situation. So 0, identically 0, and is a conservative system. Constant, independent of Xi, always having a negative sign is certainly dissipative. Having a positive sign is blow-up. But the point is that if this happens, very good. May not happen. For example, the situation which we discussed qualitatively yesterday, that x dot is equal to x minus xy, y dot is equal to minus y plus xy. If you calculate the divergence del x dot del x plus del y dot del y, then that's equal to, so 1 minus y minus 1 plus x is equal to x minus y. So it's a function of coordinates. It's not identically 0, neither is it a constant independent of x and y. So you are stumped at this point. But it's a conservative system. Why is it a conservative system? Because I can actually integrate and write, I can just write dy dx is equal to y into x minus 1 into x into 1 minus y. So dy into 1 minus y over y. So it is 1 over y minus 1 is equal to dx into 1 minus 1 over x. So log of y plus log of x minus y equal to constant. So I have a conserved quantity. So it's a conservative system because I can actually construct an integral of motion, a constant of motion. So at the end of the day, if I'm supposed to find out whether a system is dissipative or conservative, if it is a conservative system, there would always exist a constant of motion. Finding it is a problem. Things would not be so straightforward. It is just that there you would always, I mean, what is the catch? Catch is that I have written this in the inconvenient set of variables. There would exist in general a nonlinear transformation which would be able to write this equation in a form from which this is going to follow. But that requires, I mean, a certain amount of insight. And so this classification, conservative, non-conservative, which is traditionally done in this fashion. If it works for you, fine. But if it gives something which is sort of neither here nor there, then you have to be very careful. You need to do a little more, probe the system a bit, and see whether you can actually get a conservation law or not. So, at the end of the day, does the system admit a constant of motion? If you can find it, it's conservative. If it is written in variables which give you a divergence of v equal to 0, very good, you are through. So that's basically all the definition. That I have a dynamical system, I have an autonomous, non-autonomous, I have conservative, non-conservative, and with that, I mean, that's all that one needs to know. And now one can simply go ahead and study these systems for various increasing the complication step by step. So, which were all one-dimensional dynamical systems. So these are all going to be, so we are going to start with a one-dimensional system, which is x dot equal to f of x. So that's one variable, autonomous system, x dot is equal to f of x, and we have to write down the give f of x, and I give you f of x, you give me x, can always be done. At the worst is that you have to do it numerically, but something that can always be done. On the other hand, it's a good thing to set all the definitions and techniques going. So we are going to do the one-dimensional case as thoroughly as possible. So x dot equal to f of x. Now, point is, all right, and what I did not mention is that for most of this course, we'll be following the text due to Stochastic very quite carefully, cover whatever is given over there, certainly. So now the point would be that before that in these the initial 3 chapters where this text deals with one-dimensional systems, you would find a lot of examples given, a lot of exercises and examples which are actually borrowed from certain areas of physics which are sort of cursorily mentioned. So it's worth our while to stop for a minute, and the point is we'll be talking about fx, which is a quadratic function that is x plus something into x squared, or a cubic, which is something like this, or something constant plus x squared, and so on and so forth. And you have to ask the question that why on earth, I mean, why are these useful, what's going on, and what's, so where is the, what's the connection with real world? So now, one dimension, dx dt equal to f of x, doesn't seem to be a physics problem. So, but it is the natural habitat of population dynamics. So there would be, so population dynamics, single species, really, and so that there is just one variable, the number of these the population at a time t, and somebody tells you what n dot of t is, and you go about so then writing down dynamics for it and going about it. So going about solving it. So n dot, for example, I mean, if you have a sort of set of bacteria or something like that which can thrive, grow easily given some whatever substrate or other, or essentially like rabbits in a grassy field, you would have some kind of a growing population, exponentially growing population, n dot equal to a times n. So very good. But suppose you restrict the amount of nutrients. If you restrict the amount of nutrients, then of course, I mean, there has to be fight. So there would, I mean, initially when there is enough nutrient, everybody would be happy and number would thrive. But as soon as the nutrient gets to be a little problematic, the amount of it, there would be conflict. Conflict would mean that you are going to decrease, people are going to die off, I mean the population is going to go down, and essentially that would be like an n squared term. If I have n animals vying for this food, it is pairwise, they are going to annihilate each other. So it is like an minus bn squared. So this is the kind of dynamics one thinks of, that population dynamics is something which a one-dimensional system, dynamical system, would be useful for modeling. So that's one category. Would there be something more interesting with a physics background which one can think of? Huh? Pardon?
Radioactivity, those kind of situations.
What's
Radioactivity.
Oh, radioactivity. Ah, that's all right. I mean, it decays, all right, but then pick that it's a linear decay. Thereafter, find it's certainly an example of radioactive decay does the job for you. But complications on that dynamics would be more difficult to find. So, all right, that's certainly one example. It's also a population kind of business because it's a number of nuclei which are diminishing, each decaying according to that point. Let's see something else. Suppose I was doing Newton's law with a damping then if you consider the high damping limit, the high damping limit of this, Then you have somewhat more, depending on what kind of a potential I give you, you can have a somewhat more interesting dynamics. So highly damped, Newton's law in the high damping limit can be a candidate for such things. Now, does Newton's law operate in a, that is, if I take a simple harmonic oscillator, for example, would it operate in a high viscous, in general, operate in a high viscous situation? Well, can be made to. I mean, people have actually done these experiments with polystyrene beads in a confined in a region with a medium which produces a viscous damping, and seen the effects of the one-dimensional, the damping over damped region very cleanly. But that's again, I mean, sort of also a little bit contrived. Something more natural is systems for which one does StatMech in a somewhat strange way. Let's bring. So I would like to take 5 or 10 minutes, I mean, to actually bring out this part of it which can be sort of, which actually gives the reason behind a lot of the examples that Stochastic talks about in this, in these 3 chapters. So, all right. So imagine that I have a set of independent particles in thermal equilibrium at a temperature T. So imagine, well, all right, what do I know about them? What I know about them is there is equipartition of energy, and half mv square average, it would be 3/2 kT. This is in a box. V square is Vx square plus Vy square plus Vz square. Very good. All right. So that's what I know about this. Now, what kind of dynamics? Suppose I were to focus on one chap of, so one chap of mass m, and what kind of a dynamics does it have? So let's look at this one particle which at any given instant is probably trying to move with a velocity v. Now there would be all these other particles which move around and are going to come and strike this chosen particle. I've just tagged a particular particle, and at this particular instant this particle is trying to drift with a velocity v, and all the others are going to try and come and hit it. Well, on an average, so there would be, I mean, if I were to try and write down Newton's law for this, I would have to certainly add a sort of random force coming from the random hits that these other chaps are executing. Except that apart from this, there is another part of the force which is not so random. Because as this chap tries to drift, if it is trying to drift in this direction, there would be more hits from the forward than from the back. So if I look at the momentum transfer per unit time because of hits from the front and hits from the back, then I would find that there is a larger number of collisions coming from this side, coming from the oncoming molecules, than from those coming from behind, and therefore there will be a tendency to retard this chap, and that retardation would be some gamma which you could calculate in terms of the coefficient of restitution or some and things like that, and you would get m dv dt is minus gamma v. That's because of its motion, and the impingement, random impingement of the other molecules. The motion is going to be preferentially stopped, so it is minus gamma v. And certainly there are the random hits apart from, this is out of those random part, I've extracted a part which is going to try and damp out this chap, and the rest of it is going to be f of t. Some random. Good. So given this, you can write down the solution. I can immediately write down the solution as v of t is integral from some initial time, call it 0, up to t, e to the power minus gamma over m, t minus t prime, f of t prime, dt prime, plus v at t0. So that's the solution of this differential equation. So that's the solution, and I can construct. So where am I headed? I want to head towards this. So let me get rid of the vectors and just go with the one-dimensional chap so that I don't make life simple for myself. Just each dimension is separate, so I just do it for one of the x, y, z directions, and I look at v squared t. So I look at v squared t, and I'm going to average. I'm going through this rather fast because this has nothing much to do with what we are eventually, this is just a motivator rather than anything else. So there is going to be one term like this being multiplied by another term like this, which means I have 2 gamma over mt e to the power gamma mt prime plus t double prime, and it is ft prime ft double prime dt prime dt double prime. There would be cross terms, but this f of t on an average is 0. So the only non-zero part of the f, which is this resistive thing, has been taken out. So f of t, the other are pure random hits, and that's going to be average. That's average is going to be 0. So cross terms are going to be 0. Sorry, I should have had e to the power minus gamma over mt over here, and plus e to the power minus 2 gamma over mt and v squared at t0. Yeah. So that's v squared t averaged over that noise over there. Now you play start playing the. I have to say something about this noise, otherwise I'm stuck. So you make the usual statements. F of t is Markovian. That is only t, and it is uncorrelated at two different times, so the correlation carries a delta function, delta of t minus t double prime. It is Gaussian, which means that I only need to prescribe this and the second moment, and I know all the moments thereafter by saying that it's a Gaussian. So there is a delta function, there is going to be some strength d. The delta function reduces this integral, one of the t double primes gone, you just have one of these left over here, and there's the strength of this d, which is the strength of the get ready with it is dm over gamma, so you are integrating out this. You have 2 times gamma over m t prime, so 2d, 2 gamma cancels out, so it's dm over gamma, that is e to the power minus 2 gamma t over m, and then this integrates out to 2 gamma t over m minus 1. So t prime integrated from 0 to t, so it is e to the power 2 gamma t minus 1, and plus this chap over here. So you take the limit of t going to infinity. So if I wait long enough, then this is 1, so that's the survivor. This damps out this one, this damps out that, and so the long time limit is going to be, so the long time limit of this answer is going to be v squared average is equal to dm over gamma. So that's the way things work. And if I choose now this d over gamma correctly in terms of the in terms of this temperature over here, the choice of d over gamma would tell me correct. I choose it in such a way that this is equal to half mgx squared is just half mgt. So this is how it goes. So this is the way that this relation with the dissipation over here, m dv dt minus gamma v plus f of t, gives you with this correct choice of f of t, it's the right kind of statistical mechanics that you eventually land up at t going to infinity. The stochastic dynamics takes you to so alright, now this is something which does happen. And similarly, therefore, if this v is just incidental in all these things, if I had a dx dt which is equal to minus, had an equation of this kind, minus dv dx plus some kind of noise, which the right kind of noise, which is some kind meaning this kind with the coefficients correctly adjusted, then I would find that there is equilibrium distribution for x, which is going to be equal to e to the power minus v over kt, give or take factors of 2 and so on and so forth. So there would be a dynamics which is dx dt equal to minus dv dx would lead to an equilibrium distribution which is this. So coming backwards, it is that if somebody tells you that there is a system with a potential, under a potential V, which has an equilibrium distribution given by this, then you can say, aha, then in that case, I must have started with dynamics which looked like this. So I'm reversing the whole business. I show you this thing going one way, and now using this, having shown it to you this way, I can tell you that, all right, I mean, if somebody tells me that there is this distribution over here, I can go back and say, aha, there is a dynamics which looks like this. Now, this is true for, I mean, you did it for V over here. Okay, why is this, and I skipped a few steps here, got the Maxwell Vx square, and that does not mean that the distribution is mv square over 2kt. You can actually calculate all the moments over here and see that the distribution is actually that. So this is just the first moment calculation because it's a Gaussian noise. All the other moments would follow in a similar manner so that the probability distribution is this. More importantly, if I start with this and play the game, then I would get equilibrium, which is V over kt. Here it was gamma V, and therefore it was like V, in terms of that velocity, the potential is like V squared, so you get a V squared in the, and so if I have a V over here, the V of x sitting over here, then you are going to get a dynamics which is this. Alright, so that's what happens. Now that means that, alright, suppose
Sir,
go ahead. Yeah.
Sir, you roughed it out.
What did I rough it is?
Okay, so the thing is that in V squared T average, you got. So what kind of averaging was that? Is it average over time or?
It's the average over the random force over here.
Or not over time, right?
Not over time. It's an averaging is over this random force over here. That's what I averaged over. Sorry. So that's easy to put back. So there was a f, and there was an integral which looked like minus 2 gamma over m t minus t prime. It is t over here, or rather gamma over m, 2t minus t double prime dt double prime, and the averaging v square average obtained as average over this distribution over here, and this distribution is like delta t prime minus delta t double prime, and therefore that integral is 2 gamma over m t minus t prime integral dt prime, the t double prime done over this. That's what gives rise to e to the power minus 2 gamma m over t into the e to the power 2 gamma over t minus 1. And if I wait till t tending to infinity, then v square average eventually settles down to kt over m. That's the idea. Yeah. So the averaging is done over the random force. So there is this dynamics, which is a random dynamics, and the random dynamics with the external random force prescribed in forms which we like, and that eventually. So that's that. So the point. So then going back, this simply says that, all right, if somebody says that this is at a temperature T, there is the x variable distributed as e to the power minus Vx over kt, then that would imply that the dynamics of x look like this. So that x could be anything. I mean, x is just some physical variable, and that the maths does not care about what the meaning of x is. It is just the maths that dx dt equal to minus dvx plus f of t, with f of t Gaussian prescribed in that manner. Your equilibrium is going to be that, which I am inverting to say that if I know it is this, then it's that. So why all this? I mean, why all this aside? It's because Let's suppose I was looking at, when it is dynamics like Newton's law and so on, you can write down the dynamics. There is no doubt about what the dynamics is going to be, which is that. But suppose you are dealing with a piece of magnet. So you have a magnet and near the Curie point. So for T greater than Tc, the average magnetization is equal to 0. So let me denote the average magnetization by m equal to 0, by m. So T greater than Tc, that's 0, and T less than Tc, it is m not equal to 0. So, and all this information comes from a mean field theory due to Landau, where the P equilibrium is written as e to the power minus am squared plus bm4 divided by kt, where a is proportional to t minus tc. So here is now a situation which is first pass description of magnetism, and it is so what is a magnetic system? What's one of the interesting characteristics of a magnetic system? If you are above Curie point, the magnetization is 0. If there is a ferromagnetic to paramagnetic transition, above Tc 0, below Tc that, and that's captured by a distribution which looks like e to the power minus am squared plus bm4 over kt. And if you look at v of m as this quantity over here, well, generally one puts a 2 and a 4 over here for to make life simpler on taking derivatives. Then for A positive, which is T greater than Tc, it's a potential which looks like this. For A negative, it's a potential which looks like this. And here it is m equal to 0, the favored state. Here it is either one of the up or down magnetization states which are favored. So all right, so this is this described. Then you ask the question, what was the dynamics of this? If I consider the dynamics of this system, then what kind of a dynamics did this magnetization follow? And then you say, aha, I know what it followed. It is m dot is equal to minus, this am plus bm cubed plus some noise over here. So that would be the dynamics, the mean field dynamics of a system which is making a transition from, which you are considering near the Curie point, making a transition from T greater than Tc to T less than Tc, from A positive to A negative, making a transition over there from a state with m equal to 0 to a state with m not equal to 0. So that would be the dynamics, and if I suppress this part over here, then that put in the noise later when if I look at it just as a dynamical system, then m dot equal to this is the deterministic part of this random dynamics over here, and therefore it's one of the examples which you could talk about in one-dimensional, as a one-dimensional system. So this is what the issue is. That this is why this detour over here to tell you that, look, I mean, there are in this initial part of Stochastic, there is a lot of systems which one talks about, which doesn't look like, I mean, it should be a one-dimensional dynamical system. It just says, look at this equation and then, but then what is the motivation for why does it make sense in a real, in some approximation, it makes real sense. In this mean field level of description of magnets, this is a decent dynamics for the magnetization to follow. Similarly, if you are looking at lasing, and the lasing has a threshold. So lasing action, there is something called a pump parameter, and lasing action begins only if the pump crosses a threshold value. Once again, it is that lasing in terms of averaged electric field square, that is in terms of the intensity. The laser intensity would once again follow a similar equation of this kind. If A is negative, then no lasing, that is the pump is not strong enough to bring about, and then it makes a transition. So this is A greater than 0, this is A less than 0. So make the pump parameter large, you have A less than 0, and then so lasing threshold is once again something which you can get out of. Similarly, you can talk about the onset of convection in fluids, that generally it's if I have a fluid taken between two parallel plates and I have this at a temperature T1 greater than T2, so I'm heating from below. It's not that any arbitrary heating can start the fluid, make the fluid convect. There is a critical value of this parameter called the Rayleigh number, which is the expansion coefficient times this temperature difference times g, the acceleration due to gravity, d cubed, divided by the thermal diffusivity times the viscosity. And it is only when R becomes greater than 1708 that you find the convection setting. Once again, ideal for a description in terms of that. That if your A is equal to R, then C minus R, then for R less than RC, it is this 0 convection amplitude state which is stable, and then you describe things in terms of the amplitude of the convection rolls, no rolls, 0 state favored for this, and then you go to a negative when R becomes greater than RC, and dynamics of this kind would tell you that now you would have a certain amplitude for the convective rolls. So this is the backdrop. The backdrop of the various examples that Stochastic will talk about. The population dynamics is straightforward. There is no catch over there. But the physics examples are somewhat more subtle, and therefore it is worth knowing that why should there be physics examples in a trivial one-dimensional dynamical system. It's because of these rather sort of behind-the-scenes maneuver which finally leads to a mean field description of physics of various kinds. So this is going to be, I mean, what is a mean field description for magnet over here? Similarly, it's a very strongly averaged out description of the electric field in a laser, and similarly for the velocity field in the fluid. So it is all some kind of a mean field approximation, and in that mean field approximation, when you talk about the field, it is going to be looking like that. So all right, so that's, I mean, essentially trying to give you a picture of why one talks about these things at all. I mean, normally one would have said that talking about a one-dimensional system is quite useless. But the point is, it's not as useless as it would appear. Alright, so that's the, so now back to business. So one-dimensional system x dot equal to f of x. Now what are we supposed to do? Let's start with in x. So the first thing would be that f of x is a constant. That's much too trivial to take into account. So the next is constant plus x. The constant can be removed by a shift. So it's x dot equal to lambda x. So that's the, and what did we see yesterday? That if lambda greater than 0, x goes off to infinity. If lambda less than 0, x goes to 0. But if your initial condition is x0 equal to 0, then you stay put, right? So that's this is the only interesting part, that if my initial condition is set over there, then I don't move away, I can't move away from there, because if you try to compute, your x dot would always be 0 and you would never move in forward in time. So x dot equal to f of x of x0 equal to 0, that gives you, depending on how big this polynomial is, a set of x0, and we are only interested in the real ones, because this is dynamics along the real line, and you are interested in the real roots of f of x. So you have a set of x0 which are fixed points. x0 are fixed points of f of x, which means if you start out from there, you are not going to move it. If that's your initial condition, you don't move at all. And now comes the next question. What if I start in the vicinity of it? Suppose I set x equal to x0 plus delta x. So x equal to x0 plus delta x, I am starting out from a vicinity of x0. Delta x is infinitesimal. And I want to see what happens. So alright, my dynamics is x dot equal to f of x, and I have put this. So delta x dot. So x is set as x0 plus delta x. x0 dot is 0, so there is no x0 dot. So the left hand side is just delta x dot. On this side is fx0 plus delta x, and I can Taylor expand this as df f of x0 is 0, so this is gone, and if I assume that this is non-zero, then delta x dot is equal to lambda delta x, where lambda is equal to df dx at x naught. So df dx at x naught, and therefore delta x, if df dx at x naught is greater than 0, delta x grows, and if df dx at x naught is less than 0, delta x decreases. So if I start at a little distance from x0, if my derivative of f is positive over there, then I'll go further away from x0. And if, on the other hand, if it is negative, the derivative, then I'll move towards x0. So here is my x0, and you have started out from here, and you will go away if df dx x naught greater than 0, and this fixed point, and you will move in towards it if the other. So in the case where df dx is greater than 0, you have an unstable fixed point. And if df dx is less than 0, you have a stable fixed point. Your approach to the fixed point is exponential. That is, your solution x in the vicinity of x0 is this plus e to the power plus or minus mod lambda t. So this is just a number. So the delta x is going to be an exponential solution, and so you approach the fixed point as t goes to infinity. So there is at infinite time you end up at x0. If it turned out that the derivative vanished, the first derivative vanished, then you would have to go to delta x dot equal to the next term, which would be delta x squared, and then depending on the sign of sign of this coefficient over here, you would either delta x would decrease or would increase, and if it increases now, there is going to be a finite time. It will run away to infinity at a finite time. So that's the examples which we encountered yesterday in a heuristic fashion. So x0 plus, this is if the initial, if the derivative is non-zero at the fixed point, then you have this business over here. So remember the example that we talked about yesterday. So that is really everything about a one-dimensional system. That you have a fixed point, you want to talk about its stability. There is just one criterion, stable or unstable, depending on depending on this derivative, you have a stable or unstable fixed point, and that's about all that one needs to know. So x dot is the example that we took yesterday. One of the examples was x dot equal to 2x minus x squared, and as we agreed that there was this point which is x equal to 2 over here, and if I started out from the right of the origin, I went towards this, and if I started to the left of the origin, then I went away to infinity. So we did not describe it in terms of fixed points, we just talked about it heuristically, that what do I expect this system to do. So today, you find the fixed points. There are two fixed points, x equal to 0 and x equal to 2. So fixed points generally x0 or x star, writing x0 is much easier. But anyway, sometimes this confusion of x0 as the initial condition and so on, so forth, so maybe a star is a better bet. But anyway, the fixed points are 0 and 2. The derivative, so this is my f of x. This is my f of x. The derivative is 2 minus 2x star. So, so derivative at x star is this. So if it is x star equal to 0, the derivative is positive and it is unstable. So if it is a derivative over here, x star equal to 2, the derivative is negative 2 minus 4, so this is going to be stable. Yeah. So what does stability and instability tell you? It tells you that here in this, on this line over here, I have origin and I have 2, and it's linearly stable, linearly unstable, which means if I start out in the vicinity of this, then I'm going to move away, and if I start out in the vicinity of this, then I'm going to move in. Right? So this is only a statement. The stability analysis that we have done is only a statement about the immediate vicinity of these fixed points over here. But if I'm sitting in, if it's a one-dimensional line, life is absolutely easy, because if it so happened that when I move far away, this chap is going to turn back, then it means that I must have a fixed point over here. So similarly, it can't, this trajectory over here, you can't be drawing an arrow to this side unless I also put a fixed point in this region, and therefore what is locally true is going to be globally true at least till you hit the next fixed point. So 1D is absolutely straightforward, that you go ahead, find all the fixed points. Fixed point number 1, 2, 3, suppose you have, I have given you a horrendous f of x and you have found a large number of fixed points. Well, now, are they stable or unstable? You need to test the stability of only one. Suppose I test the stability of this chap and find it unstable, then the next one has to be unstable. They have to alternate. Yeah, because if I had two successive s, then it would be locally this and locally that, and that would mean that I would have to put an unstable one in between. So if you have, so 1D calculation wise is again, tremendously easy, because I need to find the stability. If I find a large number of fixed points, all that I need to do is find the stability of only one. And that gives me the entire picture. So, remember the other chaps which we did, x dot equal to 1 minus x squared, that had the fixed points are x star equal to plus minus 1, df dx is minus 2x star, so x star equal to 1 is stable, and x star equal to minus 1 is unstable. So here we are, minus 1 plus 1, that's origin. So these are the two fixed points over here, and you so that's how you go. x dot, the other thing we did was x dot equal to x minus x cubed. So df dx is 1 minus 3 x star squared, and x star was 0 and plus minus 1. So df dx, so x star equal to 0 is going to be unstable, and x star plus minus 1 stable. That's why, so here's my origin over here, one of the fixed points, here is 1, and here is minus 1. So I started out from here or here, I ended up over here. Started out on the negative side, I ended up over here. Very good. So that's the whole bit. So I give you x dot equal to df dx. There is really nothing in it to calculate, to understand the dynamics. You just have to find the fixed points, calculate one stability, look at, and that's it. Now, what, where, why look at it? How does one introduce the complication? The interest comes if I have in this f of x, there exists, x is the variable, but there exists a parameter which I can do. You know, a parameter which can be tuned by any of us. That was the whole business about this magnetization game that I was playing. That I had a parameter which was T minus Tc, and by changing the temperature I could make it positive or I could make it negative. So there exists, this whole business becomes somewhat more interesting if I have a parameter R which is tunable, and that is tuned by whoever gives you the system, and there is a variable whose dynamics you are going to look at. So I have a parameter, and now that parameter brings in extra nicety. That is why these systems, even the one-dimensional systems can be interesting, that with the parameter you can have changes in the dynamics of the system. So I'm looking at dx dt. Instead of looking at 2x minus x squared, or 1 minus x squared, or x minus x cubed, let's look at, to begin with, Rx minus x squared. So dx dt is equal to Rx minus x squared, where R is a parameter which you are going to tune. So alright, what are the fixed points? It's all very straightforward, but at least it's going to show something which is less trivial than what we have been talking about. So the two possible fixed points are x star equal to 0 and R. Now you want to look at the stability. So stability, so this is my f of x, and I can calculate df dx minus r, and so this is going to be stable if r so it's r minus stable if r is greater than 0 and unstable if r is less than 0. So you see, I have carried out, I have a switch in the stability pattern. I have a switch in the stability pattern as I change r. So here is R and here is X star. So one fixed point is 0. So X star equal to 0 is one fixed point. The other fixed point is R. So that's the 45-degree line over here. Okay. So I have the 45-degree line over here, which is the other fixed point. So X star versus R, and when R is negative, X star equal to 0, this is stable. And when R is positive, this is unstable, and this is unstable here, and this is stable over here. So if I look at this X star versus R plot, I find that if I'm allowed to tune this parameter over here from negative to positive, then there will be a switch in at R equal to 0. There is so at this point R equal to 0, there is a change in the stability pattern. The number of fixed points over here has not changed. I had 2 before, I have 2 after. That is for R negative, I have 2 fixed points. I have 2 fixed points for R after, for R positive. So the number of fixed points hasn't changed, but there is a change in the stability, that this at R equal to 0, this change in the stability pattern is called a bifurcation. So change in the stability pattern, in general, a bifurcation can be a change in stability pattern, a change in number of fixed points, or both. So I either change the stability pattern and keeping the number of fixed points same, or I change the number of fixed points well, if I change the number, generally, I mean, it would mean that the stability pattern would get changed. But all right, I mean, imagine that if, suppose I had something stable, generate new fixed points which are unstable, maybe one such example would be there. So it could be change in number of fixed points without really changing stability in some fashion or another. Or it could be both. There is change in stability pattern, or there is change in and there is a change in the number of fixed points. So whenever these things happen, they call that, you call that a bifurcation, a change in the number of fixed points, the stability pattern, or both of them. That's what is called a bifurcation. And in this particular case, where the number of fixed points have not changed, they have just exchanged their stability. One calls it a transcritical bifurcation. So this is, yes, nomenclature, nothing else. So it's a transcritical bifurcation. I have no idea why it is called transcritical. I mean, anyway, what it is an exchange of stability. All right, happen for Rx minus x squared. What would it still happen? The important thing is that suppose this was suppose this was dx dt equal to Rx minus x squared minus ax cubed. Would it still be this?
So the total thing, Rx minus x square minus ax.
Huh?
Ax will be.
What happened?
Oh,
Huh? Plus, I mean, you have thrown in all the higher powers. And the question is, can I still talk about dx dt equal to Rx minus x squared as the canonical form for this particular bifurcation? Imagine that you are near the transition. So transition is occurring at r equal to 0. Transition is at r equal to 0 and you are near r equal to 0, which essentially means that x is small in some sense. So x is small in some sense, and so you can get an intuitive feeling that, all right, I mean, maybe the x cubes and x fours and so on would not be so important. That if I'm in the vicinity of r equal to 0, maybe, I mean, this Rx minus x squared is all right as a description. You can make this a little more formal by saying that let's imagine a transformation from x to a variable y, which you call y equal to x plus some alpha x cubed. It is supposed to be a almost near identity transformation. So y equal to x, that would be identity transformation. And I have added in what I imagine is a small quantity, alpha x cubed. So I'm imagining that I have done something not too wild. That it is y equal to x plus alpha x cubed, and let's see what happens.
Sir, this is near x equal to 0.
Huh?
This is near. This is r equal to 0.
What?
He's asking, is this near r equal to 0? I'm doing this one.
I have not yet made, it would be near, as I said that I expect that if things are near r equal to 0, x would be small and I would be in good grounds. So I want to test it out. So I'm making a transition to a variable x, to a variable y, which I believe is going to be close to identity, the transition. So I'm writing it as y equal to x plus alpha x cubed, and let's see what the dynamics in y is. So I go ahead and write y dot is equal to x dot, which is Rx minus x squared so y dot is equal to x dot plus 3 alpha x squared x dot, which is equal to, now it's an x dot over here, which is Rx minus x squared minus ax cubed plus things which are ordered that, plus 3 alpha x squared into
Alpha Rx is x dot is
is x dot, which is rx minus x square minus ax cube, and then there are terms which are order x4, and then this is 3 alpha x square x dot, and x dot is rx minus x square, and so on. So here we are. If I were to invert this x over here, so here is rx minus x square minus ax cube plus 3 alpha r x cubed over here. And now let me, if I were to invert this relation, which is x equal to y plus, so this inverted, this is would be x equal to y minus alpha y cubed. So you go ahead and write this as, this is equal to ry minus alpha r y cubed. So that's the first term, minus x squared, which is minus y squared, and then x squared would mean that the next term is like y to the power 4. So that's y to the power 4 minus ax cubed, which is minus ay cubed, and the others are higher power, and then it is plus 3 alpha r y cubed plus order y4. So now you have ry minus y squared and minus alpha ry cube minus ay cube plus 3 alpha r over here. So you can, that is 2 alpha r. The y cubed has the coefficient 2 alpha r minus a, that into y cubed. And I can choose my alpha. So you can choose your alpha to be, so the choice of 2 alpha r equal to a is going to remove this y cubed over here. So that's your, with that choice of alpha, you are going to be able to shift this whole business to a form where it is ry minus y squared plus order y to the power 4. So what I am telling you is that if I have this x dot equal to rx minus x squared, I can, if I add in terms which are like x cubed plus x4 plus order x4, higher order terms, then a transformation of this variety, that y equal to x plus alpha x cubed, a transformation up to this point, I can choose my alpha in order to cast this equation as y dot is equal to ry minus y squared, and you have got rid of the y cubed term and you have reduced the correction to order y4. So this is what the order by order, you can try pushing these things, the corrections to higher and higher order, which would mean that if I were to certainly do this business close to, play this game certainly in the vicinity of x small, then you would be able to get a y which would be able to move things out to orders which are higher and higher. And so this rx minus x squared is a sort of stable description of this transcritical bifurcation. That is, if I add in a term which is like x cubed, then I can, by appropriate transformation of x, get rid of the x cubed term and put the correction to this form over here to a higher order. You can actually, and we'll do that,